We will discuss customer use cases. Our first case study covers a gaming company. The diagram shows the company's abstract architecture. We will see their specific database architecture shortly. So the diagram shows that the gaming company's high-level architecture consists of a game engine and 3 subsystems. Audience management, which manages our users' information. User reward management. This assists in keeping track of play so the system can extend rewards to users. And user tag management, which helps track users' behavior. Let's take a look at how they've arranged their databases. This gaming company was using Amazon Aurora and Amazon Redshift to store their data. We called out this situation previously. It takes multiple database systems, not just database instances, to handle OLTP and OLAP. Remember, this increases expense and makes it difficult to manage because you must learn multiple database environments. So, a little bit of background. Amazon Redshift is a cloud-based data warehouse service designed for large-scale analytics and reporting. Redshift users commonly report performance issues. Users also report issues with data management, specifically loading, unloading, and updating data. Other users have commented on the steep learning curve required to learn Redshift. Finally, while some users find Redshift cost-effective, many large users find it very expensive. Amazon Aurora is a cloud-based relational database designed for high availability and fast response times. Many users are hampered because Aurora doesn't offer the same features as other databases. This makes it difficult to migrate environments to Aurora. Aurora provides limited configuration options as well. This makes it less flexible than other databases. Finally, and this is a big one, like Redshift, Aurora is expensive if your environment houses a lot of data. We also mentioned that when you use multiple databases, you must do ETL, which also adds expense. This system design is a great candidate for database consolidation. We know from our previous discussions that the subsystems will have varying levels of criticality and that TiDB can effectively allocate resources to meet this requirement. We've replaced Aurora and Redshift with a multi-tenant TiDB environment. The customer is pleased because throughput increased by 3 times, the system has horizontal scalability, they have experienced 0 downtime, real-time hybrid transactional analytical processing, or HTAP, has made their lives easier, operation tasks have been simplified, and they didn't have to change their application to get this new system up and running. Let's discuss a second case study. This customer had more than 100 MySQL instances. This customer was facing a situation like the one in our first case study, but on a much larger scale. The sheer number of MySQL instances makes monitoring, troubleshooting, upgrades, and security a challenge, and a challenge may be putting it mildly. Not only were there numerous MySQL instances, they had a lot of data too. 330 plus terabytes, and this includes a 3-month window of hot data that all combined reached approximately 80 terabytes. This company was a great candidate for a database consolidation project. Let's see how they handled it. They moved their 100 plus MySQL instances to TiDB. They gained the same benefits as the gaming company we previously discussed. So let's talk about these out of order. Consolidating their databases reduced operation and maintenance complexity, and it improved efficiency. These factors drive down costs too. Business isolation. They maintained their previous model of keeping their business data separated from other data. Let's return to the first bullet. Cold and hot data storage tiering reduced storage costs. Separating hot and cold data allows us to store cold data on lower cost HDD drives. And not only are HDD drives less expensive, they provide greater storage space. Recall that cold data is not accessed often, and when it is, a lesser level of performance is acceptable. This strategy enables customers to save money by using less expensive drives. Look at the left-hand side of the diagram. You'll see the word hybrid. Business 1 and 2 are not vital to the overall business of the organization. They have low data volumes and aren't used often. This customer used a hybrid approach for these databases. They deployed them on a single TiDB node. Compare this with business 3 and 4. They were deployed using the exclusive model. Each of these databases TiDB nodes exclusively dedicated to each of them. Business 3 has TiDB node that only it uses, and Business 4 has TiDB nodes that only it uses. This results in physical isolation of databases from other businesses. Notice that the hybrid and exclusive approaches both use high-performance disks. In reality, these are SSDs. Finally, the cold data area is placed on a dedicated TiDB server, which run low-performance disks. In this case, they are HDDs. I have a question for you. Can you remember how we separated hot and cold data? If you said placement rules, you are correct. Let's take a moment and summarize what we've learned. We've covered a lot during our discussions. Let's review some of it. First up, cost and efficiency. We discussed how database consolidation can help us reduce costs and increase efficiency. TiDB's separation of compute and storage comes into play here. If we need more compute, we add compute. If we need more storage, we add storage. Next, isolation. Each database may have different performance characteristics, data volumes, and availability requirements. Our new database must be able to manage these divergent requirements. We discussed how resource control, which is another way of saying I want to put something in a specific place, is controlled by placement policies in TiDB. We covered how data has different access patterns. Some data is accessed all the time and other data is rarely accessed. We call this hot and cold data. We also discussed how TiDB can implement this type of strategy using placement rules or placement policies. This leads us to differentiated high availability. Tenants will have a varying HA requirement. We discussed how TiDB enables this as well. Next, scalability. A multi-tenant database needs the ability to scale. Individual tenants need the ability to scale too. We discussed how separating compute and storage allows TiDB to scale easily. We also discussed how placement policies empower us to control tenant scaling. Translytical capability. Translytical describes a new generation of data platforms that combine transactional and analytical processing capabilities within a single system. Combining these into a single system eliminates the need for ETL. We discussed TiDB's TiFlash component and how it adds column-based analytics to TiDB. And finally, easy to operate. Going from one database management system to a single one makes learning and managing the system easier. Going from a multitude of database instances to a single TiDB cluster makes your life easier too. We mentioned several important features of TiDB as a multi-tenant database: resource control, placement rules in SQL, and HTAB. Here we provide hands-on experiments for all of these features, so you can follow the step-by-step instructions and experience these functions in your own environment. Thank you for taking the time to complete this training. We hope that you learned a lot and enjoyed it.
If you want to learn more, scan this barcode and then you can get access to more PingCAP training and certification resources.